Hi everyone, we're finally starting year, and the topic we're covering today is tympanic membrane and the ossicular system. Now, for the conduction of the sound from the tympanic membrane to the cochlea, there's a very important role of the middle ear, especially the ossicular system. So let's discuss that in detail. What are the ossicles? Ossicles are basically present in the middle ear. Here you can see. Now, these are the three bones, three very tiny bones called malleus, incus, and stapes. MIS. This is the mnemonic that you can keep in mind in order to learn the names in order. Malleus, Incus, and Stapes. And yeah, so these bones, they're part of the ossicular system. They're ossicle bones, basically ossicles, and they're in the middle ear. This is the external ear, this is the middle ear, that's the inner ear. And this is the tympanic membrane, which is also known as the eardrum. We very commonly do say eardrum, but we never knew that it was called the tympanic membrane in anatomical language. Now, what's the role of ossicles? Ossicles basically help to conduct the sound from tympanic membrane to the cochlea. Cochlea is right here. That's the major role of uh, these ossicles. The conduction of the sound from tympanic membrane through the middle ear to the cochlea. Now, attached to the tympanic membrane is the handle of the malleus. So, this is the handle or the manubrium of the malleus, which is attached to the tympanic membrane. Now, the tip of the handle of the malleus, it's attached to the center of the tympanic membrane, and at this point of attachment, it is constantly pulled by the tensor tympani muscle. Which is the tensor tympani muscle? Right here, which is also attached to the manubrium of the malleus. This basically does what? It constantly both of these, the muscle and the handle. So basically, this inserts into the handle, and this causes the tympanic membrane to be tensed at all times. So it keeps it very, like, stretched out, and this tension allows the sound vibrations on any portion of the tympanic membrane to be transmitted to the ossicles. In case if this membrane was lax, it was very, like, not rigid, it was not tense, if it was very lax, so the sound vibrations would have not be able to transfer as well or transmit as well. So thanks to the this muscle, the tensor tympani muscle, which inserts onto the handle of the malleus, and this does what? Again, let me repeat those lines. That is the tip end of the handle of malleus. It's attached to the center of the tympanic membrane, and this point of attachment is constantly pulled by the tensor tympani muscle, which keeps the tympanic membrane tense. That's about this. Then this malleus, it articulates with the incus with the help of minute ligaments. Then the incus, it articulates with the stem of the stapes, and the stapes faceplate, this thing right here, the faceplate, it articulates with the oval window of the cochlea, of the membranous labyrinth of cochlea. Labyrinth means a maze, right? So moving on. Now the ossicles of the middle ear, they're suspended by minute ligaments that basically helps to, keep this entire system together, and it helps especially the first two bones to act as a lever. Now what exactly is a lever? Now you must have seen this diagram even when you were studying physics, in that it's really difficult for us to lift this uh, rock by putting our hands underneath it, because first thing first, our hands, they're not going to slide underneath the rock. It's really hard. So because of physics, we got to know that there's something called a lever system, in which you just need a very thin sheet of, let's say, wood or whatsoever, and you need to slide that sheet or bar or rod or whatsoever underneath the rock somehow, and then there's this stone which will be kept under the bar. This stone acts as a fulcrum, right? And because of this, what happens, because of this lever system, it's really easy. You just have to apply force here, and this rock will be lifted upwards. So it makes the entire process very, easy and feasible. So these two bonds, they act as the lever. And what's the fulcrum point? This point of attachment is the fulcrum. So the force will be applied from this point, right? And yeah, so remember I told you about this muscle which holds, which inserts into the handle of the malleus, right? The tensor tympani muscle. Similarly, there's a muscle at stapes as well, which is called stapedius muscle, which is the smallest muscle of our body. And here, at this point of articulation, you have loose articular ligament, which is here present here. And let's talk about stapedius. Now, stapedius is the muscle, as I've told you here. It inserts at the neck of stapes, and it originates at the temporal bone and inserts at the neck of stapes, right? How about the tensor tympani? It originates from the cartilaginous part of the auditory tube, the sphenoid bone, the greater wing of sphenoid bone, and the bony canal in the petrous part of temporal bone. So these are its origin point, and it inserts at the manubrium of the malleus. Its function is to tighten the tympanic membrane. So here we're done with the muscles as well. Now, the articulation of incus and stapes, don't forget this mnemonic, because of the articulation of these two, they allow us to, not us basically, they allow the stapes, like they're both conjoined effort, that the stapes is able to push forward the oval window and also the cochlear fluid. They both are like together able to push forward on the oval window and the cochlear fluid. And similarly, they can also pull back on the fluid every time the malleus moves outwards. Every time the malleus moves outward, the together will push backward on the fluid as well. Now let's move on. Now the second thing we're studying today is a very important phenomena known as impedance matching. Now what exactly is impedance matching? So we do know this from our younger grades, that whenever there is any sort of, let's say, like change of medium, right? For example, let's talk about sound in this case scenario. If the sound is, let me just adjust the size. Yeah, better. Whenever the sound is traveling from a less dense medium to a denser medium, so what happens normally? For example, this is sound. It's traveling from less dense medium to a denser medium. What will happen is that some amount of the sound will be reflected back. So because of this reflection back, a very less amount is transmitted forward, right? So there's some sort of hindrance because you have changed the medium from lesser denser, we're going to a denser medium. So first, this much amount of sound was going forward, but then now eventually because of the reflection, very little sound is going forward. So you're hearing a very feeble sound. If our ear didn't know how to tackle with this, you would be hearing a very feeble sound, right? But thanks to our ear, it's designed in such a way that it knows how to tackle with this with the help of impedance matching, which is done by our tympanic membrane and the ossicles. Now, what happens is that, for example, if there's this much amount of sound that's going into the ear, what will happen is that even though if okay, so basically your ear, it's going to do what? It's going to amplify the sound much more. So let's say it amplifies and makes the sound this much. And if the sound is amplified so much, even if there's some sort of reflection back, that won't bother us. Why? Because we have sufficient amount of sound still left. So that reflection back has been balanced out by the amplification. So this amplification, it balanced that reflection out, right? I hope I'm making sense. So again, let me recap this impedance matching phenomena. It's very important. First of all, starting off with sounds. What are sounds? They're basically variations of air pressure, right? And these are transmitted by the external ear via the tympanic membrane into the middle ear and then the inner ear. These are the variations of air pressure. Now, also one more thing, your external ear and your middle ear, they're filled with air, and your inner ear, that's filled with the fluid. Very important. Now, for example, if the sound comes and it vibrates this tympanic membrane, so this tympanic membrane is going to vibrate at the same frequency of that of the sound. So if the sound wave came at this certain frequency, your tympanic membrane will vibrate at exactly the same frequency, right? Now, the next thing I told you about the impedance, let's now like recap this impedance matching phenomena. What happens is that when sound wave travels from one medium to a denser medium or a high impedance medium, these waves tend to reflect back. And because of this, obviously the energy decreases or amplitude of the vibration decreases, and therefore you're going to hear a feeble sound. But to tackle this, our body has an alternate mechanism that actually amplifies the sound before it reaches the inner ear, such that the expected loss of the signal, which is going to happen due to impedance, it's balanced out by its amplification, right? So that loss is balanced out by the amplification. Now, how is this done? Let's look at this formula of the physics, very important. Pressure is equals to force upon area. Now, fundamentally, in order to do impedance matching, you need to increase the pressure. Now, how can you increase the pressure? In order to increase the pressure, you need to do two things. You can either increase the force or decrease the area. So there are three ways to do this. What are the three ways? First is the area advantage. The second is the curved membrane. The third is the lever action. Now, this thing does what? It decreases the area. What does this do? This decreases the area, and these two increase the force. Eventually, what do? They increase the pressure, right? So that's what we want. Now, let me explain these to you in detail. So the first thing first, area advantage. Now here you can see there's a lot of area that comes in contact with the vibrations. How much is this area? It's almost 55 millimeter square, right? This amount of area comes in contact. But if you look at this, it's only 3.2 millimeter square. So your area has decreased. Because of decrease in area, what happens that the pressure increases. So a total of how much force is being exerted? Almost 22 times more compared to here, right? That's what the book says. So because the fluid has, and also why do we need this increase in force? Why is it important? This is important because this fluid has, there are two reasons why it's important. Because this fluid has a greater inertia than air. Therefore, increased amount of force is necessary to cause the vibration because of the greater amount of inertia in the fluid compared to air. So more force is required to cause the vibration. And the second reason was because of this loss. There was also some loss when you're traveling from a denser medium to a from a less denser medium to a denser medium. So this was an impedance medium, right? So you need this change in the force. So first thing is done, the area, it decreases and the force increases by 22 times. The second is the curved membrane. So this is the curved membrane. Whenever the vibration hits here, it's manifested as the change in distance. If it hits at this point, it is manifested by the change in distance. But if it's hit at this point, right in the center, this region, it's manifested not by the change in distance, but exactly by the force. So that entire thing is, it translates into increased force. That's about the curved membrane. And third was the lever action. I told you this entire point acts as a lever, and this is the fulcrum. So when this entire thing is working together, there's a lot of force. So that's how the pressure increases, right? So that's about impedance membrane. The tympanic membrane and ossicular system, they provide impedance matching between the sound waves in air and the sound vibrations in the fluid. So very important, between the air and between the fluid, there need to be impedance matching. Firstly, to decrease the um, loss, because see, this is a denser medium, right? And this is air, this is air filled, and this is fluid filled. So there need to be there'll be some loss, there'll be some loss of vibration. So that needs to be tackled by amplification. So basically, impedance. What happens in impedance is amplification. And the second thing is that uh, because of the inertia. So this thing has more inertia that needs to be overcome. Now the third thing in today's video that we're going to study is the attenuation of sound. Attenuation reflex. Also, one more thing. I had to tell you about the, okay, that I'll cover in a second. So attenuation reflex is basically also known as the tympanic reflex. Now what happens in that is, for example, if you're hearing a very loud sound and it is transmitted to the ossicular system, and from there into the central nervous system. So first a very loud sound, it goes into the central nervous system. You'll have a latent period of 40 to 80 seconds, milliseconds, sorry. So this latent period is, utilized by your nervous system, and a reflex occurs within 40 to 80 milliseconds. And what does it do? It causes the contraction of stapedius and contraction of the tensor tympani. Because of the tensor tympani being contracted, this pulls the malleus handle of the malleus inward, and the stapedius muscle pulls the stapes outward. So this is pulled inward, this is pulled outward. So malleus handle is pulled inward, stapes is pulled outward. So because of these two opposing forces, the entire ossicular system, it becomes rigid, and this greatly decreases the ossicular conduction of low frequency sound. So it greatly decreases the ossicular conduction of low frequency sound. This attenuation reflex, it can reduce the intensity of the lower frequency sound transmission by 30 to 40 decibels. Now you might not be able to understand this 30 to 40, but it's exactly that distance which is there between a loud scream or a loud voice and a whisper. So that's the difference. Now the function of this mechanism, it has two functions. The first function is to protect the cochlea from damaging vibrations caused by the excessively loud sounds, and the second is to mask the low frequency sounds. So it does both the functions. It also masks the low frequency sounds, and it protects the cochlea from the loud damaging sounds. And why does it mask the low sounds, the low frequency sounds? In order, for example, if you're in a concert and your friend is whispering something to you, but for now, what is more important? Enjoying the concert. What is more important is listening to the singer, and there's already so much happening around you. So you just want to be in the moment and you don't want to listen to her, gossiping about someone else. You don't want that. So basically, for now, everything around you will be masked and you'll be focused on the, or let's just take it the other way. Let's think of it, if maybe your a friend was talking about something important and there's a lot of other, noise of the people around you. So whatever pertinent information is there, the important or relevant information, right now you'll be focused on that. So it masks all the neighboring sounds. So this is also the second function. And the first was for the loud sound. So the second thing, another function of tensor tympani and stapedius is to decrease a person's hearing sensitivity to his or her own speech. How is this effect activated? By collateral nerve signals. What do I mean by collateral nerve signals? The same signals that innervate the tensor tympani, they also innervate the muscles of the mouth. So as soon as you start opening your mouth to talk, your ears, tensor tympani also contracts, causing rigidity, and then you'll hear decreased your own sound, and which is good. We do not want to hear ourselves as often. And yeah, so that's pretty much it. I hope we've covered impedance matching and the attenuation reflex or tympanic reflex.